what I really wanted to talk about was complex multiplication, but I quickly realized that, well, there are a lot of somehow requirements that you have to understand first. So I thought I would just talk about Silverman's book 2, chapter 1. And again, the first half of the page, I realized he's invoking a lot of big theorems already. So we're going to take another step back now and talk about some topics of Silverman's first book. And specifically, I want to talk about elliptic curves over C. Okay. And pretty much all of what I'm going to write here, you will find either in Silverman's first book or just, the PDF I uploaded. So I like the way he introduces actually the idea of elliptic functions and elliptic curves there. If you remember maybe your calculus class, computing the arc length curve. So say a curve given by a plane curve y is f of x. There's this really simple integral formula where you just compute the square root of 1 plus y. We integrate this with respect to the x and, just on an interval. And this tells you somehow the length of this graph. Now, if you want to do this for a circle, so a circle is parameterized by this equation x squared plus y squared equals 1, a circle radius 1, then somehow the integral you will be evaluating, you can do the manipulations by yourself if you want to convince yourself, but this is somehow the integral you would be computing. So this would be 1 minus x squared. Okay? And, well, depending on how you choose your integration in borders or whatever, this will be really an arc sine. Okay. Maybe if you shift your integration borders, it will be an arc cos, but it doesn't matter. It's just up to a constant. And so if you somehow look at the arc lengths of circles, what it leads to is inverse trigonometric functions. Okay, now what's the most easy generalization of this problem? Well, you look at an ellipsis, right? So you look at this equation, x squared over a squared plus y squared 1, where a and b are somehow these main radii of the ellipsis. And again, you can normalize this a bit, right? You can set 1 to 1 and the other to some constant c, or call it lambda. And the arc length integral in this case is going to be dx over square root of, and I already used this nice normalization here. So this is x times x minus 1 times x minus lambda. Okay, for some lambda. Lambda is really going to be, I guess, b over a or a over b, depending on how you normalize it. It doesn't matter. But the key idea, or the key point here is that there is no real closed form anymore for this integral. Because, if you think about the circle integral, sure, the inverse of the circle integral is the sine. It's a nice trigonometric function. But doing this for the second integral, for this elliptic integral, is what we're going to call this integral. Yeah. There is no real nice closed form for this anymore. But it turns out, the inverse functions for this will be, given by these elliptic functions. And historically, people looked at these integrals, and somehow this is where the name elliptic functions and elliptic curves and whatever comes from. And one thing that we can already note is that if we actually look at this term here, then it's kind of what we're used to when we look at an elliptic curve. It's just an elliptic curve, the right side of a definition given in a certain form. Okay, so a different way to start this whole idea is, what if you look at this elliptic curve? You look at the elliptic curve given by y squared equals x times x minus lambda, and it turns out that over some algebraically closed field, and today we want to work over C, yeah, that you can always find this form. So you can always renormalize somehow your defining equation for your elliptic curve to have this form. And this is what we call the Legendre form. Okay, so somehow they are parameterized by lambda. Let's think about this. Let's think about this equation a bit. So I can look at the map from E to the projective line over C. And now what I just do is I just take my first coordinate. Okay. Now, turns out this is a double cover of P1. And the way you see this is, well, in general, you know, if you take the square root of the right side, you'll have two distinct points. Except, and now this is where the ramification comes in. The double cover is actually ramified. And, well, and if you look at this equation here, you will see that one ramification point is going to be at 0, one is going to be at 1, and one is going to be at lambda. And the next is a fourth one at infinity. So this is ramified at 0, 1, lambda at infinity. And I mean, seeing that it's ramified infinity is not completely clear immediately if you just look at this equation. But what you can do is, for example, you can write it down in projective form, right? So you could homogenize this by introducing the third projective coordinates there, and then you would see that you also have a root at infinity. Okay, so if you actually look at the fiber of x, so by going in this direction, you will see that for almost all x, so basically for all x except for this nice discrete set here, y has two solutions, right? The square root, and except for these points, y only has one solution, and that's why we call this a ramified cover. Okay, so somehow something splits at these 4 points. Now, what would be good is if I could delete all the whiteboard. Yeah, there we go. So now there's something that you have to believe me, okay, and you can look up why this is true in Silverman. So one can show that this differential form is a nice holomorphic differential form. Say x over y. For an elliptic curve in the function field that's being generated by an elliptic curve, this is a nice holomorphic differential. Okay. So what we could look at are integrals of this form. So we integrate from the origin to some point b, and we simply integrate omega. Okay, so p is just xy, any point on the plane, and O is just a point at infinity. Now, the problem is it's a nice integral, but it's not quite well defined. If you take this as a map from E from E into C, right? That's fine. So it's not quite well defined. Why is it? Because the square root is not single valued, right? So actually, if you write this down, this is the integral we saw earlier. This is just, you know, from where does it go? It goes from infinity to x adt the square root of e minus 1, right, if you plug in. But now the thing is, the square root is not single valued in C, right? So one way to see this is that actually if you evaluate this integral for different paths from 0 to p, it'll give you different answers. Okay, and there's this really nice suggested drawing. So let's actually see where our branch points are. So we have a branch point at 0, we have a branch point at 1, we have a branch point somewhere at lambda, and then there's a fourth one at infinity, right? So if maybe my point p, the x of my point p maybe is here, I can take different paths of integration, right? I can maybe integrate along this path, or I could integrate along this path, right? Or maybe I could integrate all the way around here and then up here along this path. And what's going to turn out is that the integrals along the alpha and the integral along beta and the integral along gamma, they will all give you a different value. Yeah. And that's just because you're integrating around these branch points. And if you actually, you know, took a class in complex analysis, this will be very clear to you. And I'm just going to assume that, you know, that you know about that. Else we can talk about the these reasons, maybe in a different lecture or whatever. Now, there's also a trick that we learn in complex analysis is how do you make these integrals single valued? Well, you have to make sure that you don't somehow integrate across these branch cuts that are being defined by pairs of these points, right? So what I can do is I can take, so what I'm going to look at, so P1 of C for me is going to be a sphere, okay? And the way I think of this is it's just, so this will be C along with the point of infinity, okay? And maybe this point of infinity is up here. Basically, if you take the complex plane, when you fold it up and you glue it together at infinity, you introduce this point. Now, let's see where we make this branch cut. So what I can do is I can make a branch cut from 0 up to infinity, and then I can make a branch cut from 1 to lambda. And because this is a double covering, I will do the same thing again. Oh, I should have drawn bigger. Let's see. We'll take a second copy of P1 of C. I'll make this branch cut construction again. Infinity from 1 to lambda. Then I will simply glue these things together along the branch cut. Okay. And what you get from this, and I will draw it here. It's sad that you can't slide these whiteboards, but anyhow. So if you glue these things together, so basically what you do is you have to think about taking a sphere and you make 2 slits, okay, on this sphere, and then take another sphere and then make 2 slits. And if you make 2 slits into a sphere, what you get is like a tube. And then what you do is you glue these 2 tubes together. So somehow you have a tube like this, right? And this one I have cut open from 0 to infinity. Then this is the second cut where I cut it open from lambda to 1. Okay, and then I glue 2 of these together again along the same branch cuts. Well, and what you get, it's just a donut. Okay, so really what you get is a torus. Okay, that's nice. So what this tells us is that we should actually look at paths on the torus to make this integral single value. Okay, and this is what we're going to do now. So let me actually delete everything and draw this torus again. We have this torus here. These are our 2 branch cuts from lambda to 1, 0 to infinity. And now I've glued it, right? So now I don't need the branch cuts anymore because now I can freely integrate. But if we look at our integration paths on the plane again, then we have 0, we have 1, we have lambda, and maybe we have infinity all the way out here. So we have this branch cut, we have this branch cut, and now we can exactly write down 2 closed paths that will be non-zero because I can fit 2 closed paths into this plane basically that integrates across branch cuts. So the first closed path is beta, and if you look at our torus beta, something like this, okay. And then there's a second closed path across branch cuts, which is this one. Let's call this one alpha, and alpha looks a bit like this, okay. So and if you look at these 2 integrals, omega alpha, or differential from omega beta, then they will be non-zero. Okay, because we're integrating across branch cuts, as you can see here, right? I mean, for beta it's a bit hard to see. It's easier to see in the drawing that you're actually integrating across the branch cut. Just draw it for yourself. But for alpha, I mean, it's immediately clear. And now what I'm going to do is I'm going to call this omega 1, I'm going to call this omega 2, and these will be the periods. Periods now of my elliptic curve P, okay, that we defined earlier. And turns out that actually alpha and beta, if you think in terms of homology, in alpha and beta they generate the first homology group of this torus. I hope some of you have seen this construction before. What I'm trying to say is if I take a closed loop on a torus, then the group of closed loops on my torus is basically generated by alpha and beta. Okay, and I can go maybe n times around alpha, and I can go m times around beta, and this is somehow the free group generated by 2 sets. or yeah, to infinite cyclic groups. And really what we should take away from this is that if I take any path from 0 or from infinity to p, yeah, they have to differ by an integer multiple combination of these two alpha and beta paths. Okay, so they differ by say alpha plus beta. Okay. So I can simply add any element in my homology group, and it won't really change the integral of my path. But that's good, right? So we said that if I integrate along two different paths, then in general it will give me a different answer. But now I actually know what I have to mod out to make sure that all the answers are the same, right? I have to mod out by these combinations. Okay, and that's exactly what we're going to do. So in other words, this integral from 0 to p omega, this is unique or well defined up to z omega 1 plus z omega 2, right? And we said this omega 1 was the integral along alpha. Integral. Okay, that's good. Now, what you can, I mean, if we want to formalize this a bit, so the way we formalize this, we define lambda, this lattice, all the integer combinations of z omega 1 plus z omega 2. In this will be some rank 2 Z module, but you will have to put a bit of work in to actually show that omega 1 and omega 2 are linearly independent. It's probably not too hard, right? Because you could argue that they're actually generated by integrating somehow across different combinations of these branch cuts. But just believe me that this is actually some nice two-dimensional lattice. Okay, lattice. Let's see. Good. Okay. Now I can modify my definition from earlier a bit. So I can define this function f now from e into c. But now what I'm going to do is I will actually mod out the lambda, right? Because we're only well defined up to elements in lambda. Okay. And what I do is I send p to this integral from O to p omega. And I have to mod out the lambda. Okay, that's better. Now we at least have a nice well-defined integral. And now there's something really fun that you can do, okay? So what you can look at is you can actually look at this integral. Integrate from O to P plus Q of omega, okay? And now we all know that we can split paths up. So we can actually integrate from O to P. We can also integrate from P to P plus Q, right? And there. And then we can modify our second integral a bit. So we can just shift everything by Q, by P, right? So this will be the integral from 0 to Q, and then I shift my differential by P. And this top P just means translation by P, right? And I mean, you just pull back this differential along the translation by P map. And then what you can show, again, I'm not going to show this, but you just have to believe me that actually omega is translation invariant. Okay. So omega is translation invariant. Well, therefore, this whole thing is just omega. And what you get in the end is OP omega OQ omega. Okay, and what this is actually is the group law in disguise. Okay, so this just says that, I mean, I can represent my points now by this integral. I can represent the point P by the integral from O to B, and I can represent the point Q on the elliptic curve by the integral from O to Q. And this all just says that there's a nice group law where I can actually add these points and I get the third point. Or in other words, that this map F is actually just a homomorphism. Okay, that's good. Now, are there any questions up to now? Okay. there are no questions, then I will just continue. So some facts, and we won't prove those. We will actually look at them from a bit of a different angle. But it turns out that F is actually an isomorphism. Okay, so it's really true that elliptic curve over C is in a sense isomorphic via this map to this torus. Okay, and maybe I should draw a picture because this is something. Oh no, this is something that that will reoccur multiple times. Why do I call this a torus? Okay, so the way you should think of lambda is really somehow a lattice. Okay, so I have a direction omega 1, and then I maybe have a direction omega 2, and you know lambda were just these combinations omega 2, right? So what happens is that somehow these points create this tessellation in the plane, and all of these you know, these are the same vectors, and so on and so forth. What happens is in C, this creates this nice tessellation in the plane. And now if I mod out C by lambda, then really the thing that remains is one of these squares. Okay, so I can take out one of these squares, so it will be the square. Well, now the thing is actually that you have a few identifications, right? We identify these two sides because we mod out the lambda, and we also identify these two sides. Okay, and then again, if you roll this nicely up, then the thing you remain with. The thing that remains, there we go, is this torus. So that's why we call this object here a torus. Just this is just how it works out. Anyhow, so what did I say? So F is an isomorphism. So when we talk about elliptic curves over C, we can really talk about tori like this. Okay, that's nice. And so it turns out that C over lambda is a nice compact Riemann surface. Okay. And that's actually if and only if lambda is a lattice. I mean, you could maybe convince yourself by saying, yeah, if lambda weren't a lattice, so maybe omega 1 and omega 2 are linearly dependent. Yeah, this construction wouldn't really give you this nice torus. I.e., yeah, just said, right? I.e., if omega 1 and omega 2 are linearly independent over R, that is, right? So the way you could normalize maybe is say you could just take omega 1 is 1 and omega 2 is any complex number, right? That would give you a nice lattice. Okay, but now we looked in the direction of the trigonometry. So what you should think about doing this direction is somehow looking at the arc sign, right? You really look at inverses of trigonometric functions, but the way we actually want to look at this is inverses of our elliptic integrals. We want to somehow work with the trigonometric functions. And these inverses, what we're going to call them are these elliptic functions. Okay, so some ground rules that we have set up now. Yeah, we now have an idea where elliptic curves and elliptic integrals come from. But now what we want to look at is actually inverses of these elliptic integrals. And this is going to be the elliptic functions. Okay, so now we're interested in inverses or elliptic integrals. Okay, and this is going to be elliptic functions. Okay, and I mean, I'm a bit, it's a bit sad that I had to erase all of this, but if you think back, all of these things are defined up to a multiple of lambda, okay? So I could make a really abstract definition of an elliptic function is just a function that's invariant under addition of the point in this lattice, okay? So again, think of a lattice lambda, which is just z omega 1 plus z omega 2 into set. Then an elliptic function for me is just going to be a meromorphic function f of z on C such that, and again, what do we want? We want this to be invariant under the addition of points in our lattice. Okay, so we want that f of z plus omega is f of z for all points omega in our lattice. Okay, and now what you can do is you can look at the set of all these elliptic functions. And we're going to denote this by C of lambda, and this will be all the f's such that f elliptic with respect to lambda. And it turns out, so one can show, I'm just going to state this as a fact, this is a field. Okay, I mean, sure, if you take two of them and add them, I guess it's fine. If you multiply them, it's probably true. You have to do a bit of work to show that they are invertible, but I mean, we assume they're meromorphic, so they should have nice inverses and whatnot. So I guess you can believe me that this is a field. Now, I'm just going to skip the proposition here. It's not super interesting, I think. So let's look at this little theorem here. What I'm going to do is I take any of these elliptic functions, respect to lambda, and then a few things are going to be true. So the first thing that's true is that if I sum over all the residues of these functions, sum over all the residues is going to be 0. And here I will always sum over all points in this fundamental domain. Okay, this just means that sum over all points in one of these squares. Okay, and it's also certainly true that we look at the orders of vanishing of this function, and they are 0 again. And by order of w of f at w, I mean the order of vanishing. I believe this is a common definition from complex analysis. I mean, at least for us, this is going to be, and it just means that somehow, if the order of vanishing is positive, then we have that f at omega has, say, an nth root. Okay, and if the order of vanishing is negative, then it just means that 1 over f at omega has an nth root, or f at omega has a pole. This is just what this is going to mean for us. And there's also a third thing that we may or may not need later, namely that the order of f times omega itself, this always lies in lambda. Okay, and then I think Sam last week told us a bit about devices of what did we do? Higher genus curves, and there's a similar construction that we can do here. Okay, so what we're going to define is the divisor group E over lambda, and again this is the group formed by these linear combinations. And again, these are just formal linear combinations. They don't mean anything. It's just a symbol to write down a collection of points, really, and attach some data, namely some integers. So a divisor for us is just going to be the sum. We'll write m omega at the point omega, and again the sum is over all omega in C of lambda. But now because we have a sum here, so really this should be some finite object. So we actually want almost all n omegas to be 0. So such that all omega 0. And by almost all, I mean all but finitely many. Okay, because otherwise it would have to talk about products, and that might lead to complications. But we really want to have some finite sums here. And again, same as last week, or actually the week before, we can define the degree of the divisor. This is just summing up all of these integers. And then I can also define all the divisors of degree 0, very similarly to what we did. All the d div is the degree. Okay. And again, for the functions in now I'm only interested in invertible ones. I can define the divisor generated by this function, the sum over the order of vanishing of f at omega. And then if you think about the elements in here, there's some meromorphic functions, so they should have a finite number of zeros and a finite number of poles, which implies that, again, this is a nice divisor and that the sum is finite. Okay, and then turns out that there's some nice short exact sequence. It looks as follows: A star, lambda star, into lambda 0. And then there's the sum function. Brings me back into C lambda. And I should probably say how the sum function is defined. I'd like to do it all on the same page here, so we'll make sure I have a bit of space. So sum of a divisor of this form. Oh, sorry, this is an yeah. This is just really taking the sum of the points now. Okay. In C mod lambda. Okay. And so this is short exact, or it's not short, it's just exact, right? This is a theorem, so there's a bit of work that you have to do, right? This is devices of functions. But now what does this imply? The implication is that for exact sequences, then this object here will be actually isomorphic to this mod, the image here. And what's the image here? Well, the image are all the principal devices, right? So again, as last time, I could define this group prim C mod lambda, all the devices, and div 0, such that is the divisor some function. Okay, so what we find is that C mod lambda is isomorphic to div 0 of C lambda mod these principal devices. Okay, and this is very analogous to what Sam showed us a few weeks ago. And you can think of this as somehow another hidden definition of the group law in a sense. But all we have here is really that somehow you can think of this torus as being isomorphic to this divisor class group. Okay, I mean that's one nice thing that we get. Okay, now I'm sure some of you are eager to actually see what elliptic functions look like. So there are a few standard building blocks for them, and it might look like little when we mention them here, but you have to realize that there is a lot of machinery and a lot of somehow historical development that had to go into defining things as nicely as we are able to do them now. Okay, so I make this definition here. I say lambda lattice. Then we have this Weierstrass P. P. Okay, and this is defined as follows. The Weierstrass P variable z with respect to the lattice lambda is 1 over z squared plus the sum of the lambda should be a lambda. There we go. Such that point is non-zero, because otherwise we'll have a pole. So 1 over square omega square. Okay, and I mean this term here is for normalization and to make sure everything converges nicely. And usually when you define this function in the same somehow breath, you also define these symbols g2k lambda, and they are just again functions for all points in my lattice. These things we call them Eisenstein series. Okay. Now, why am I introducing them? So I'm introducing them because there's a theorem which says that C lambda, remember these were all the elliptic functions with respect to this lattice. This is actually generated by the Weierstrass P function in derivative. Okay, so this is actually generated by P of Z, B prime of Z. Okay, that's good. So now we have a basis which we can use to write down arbitrary elliptic functions. And a nice thing that you might find by somehow studying this Weierstrass P function is the following equation. Namely, it holds that consider the derivative of this function. If you square it, then this is going to be the same as 4 times p z cubed minus 60 times g4 of lambda times p z minus 140 times g6. Okay, and sometimes you redefine these constants. The first one usually we call g2, and the second one we usually call g3. Okay, so really what you get. And now let me call this thing y, and let me call this one x. So what do we find? We find y squared equals 4x cubed minus g2x minus. Aha, this is an elliptic curve. Curve. Okay. Now that's quite cool, because what does this give me? This gives me a nice map, right? It gives me a map from C mod lambda from my torus into an elliptic curve defined over C. And how does the map look like? Well, I'm sending my complex number Z in the torus to this projective tuple. I'm sending it to P of Z, prime of Z, 1. Okay, and it turns out this is an isomorphism. Okay, this is another theorem. So again, you have to do a bit of work to show this. But that's quite interesting. So see where I am. And if you think about, this is actually the other direction of what we looked at earlier, where we had this equation. Remember when we defined this function? I'm going to write it up here so we have it in the same page. We defined the function f from E over C into the torus by sending P to this integral O to P omega mod lambda. Right? So now this function phi is inverse of this function up there. So this really now creates the connection between elliptic curves over C and complex tori. And then if you trace through the definitions, of course, there's lots of what you have to show. But if you do this actually nicely, and if you're a bit careful, then you can show that these are inverses of each other. And now this creates this nice correspondence between elliptic curves over C and complex tori. And that makes somehow analyzing the properties of elliptic curves over C much easier, because you do not have to. I mean, it basically gives you a connection between somehow algebraic way of thinking and an analytic way of thinking. And there's actually a cool theorem that I'm going to write down now, which highlights this even more. Okay, and the theorem goes as follows. So if I take two lattices, lambda 1 and lambda 2, over C, then we have this theorem. I call it triangle in my notes. Namely, the set of all alphas in C such that alpha lambda 1 is contained in lambda 2. This is in one-to-one correspondence to holomorphic maps from C mod lambda 1 into C mod lambda 2. They send the origin to the origin. Okay? And then there's a second correspondence. Let E1, E2, else corresponding to lambda 1, lambda 2. Right? We now have this correspondence by what we looked at earlier. Then again, we have the following correspondence between sets, namely isogenies. Maybe we will look at isogenies in a later talk a bit more clearly, but somehow the way you should think of isogenies are the morphisms of the categories we're thinking. Like the categories of all elliptic curves, somehow the morphisms here are isogenies. I mean, I think this is a good way to think about it. Isogenies from E1 to E2, again, they're in one-to-one correspondence to the same set up there. Holomorphic maps. Lambda 2, let's try it again. 5, 0, 0. Okay, and really isogeny, all you should think of algebraically, it's a surjective morphism which sends 0 or the origin to the origin. Okay, and this is the algebraic definition, and this here is an analytic definition. And actually, what this part of the theorem is something, if I'm not mistaken, I can't remember which mathematician defined this, but this is a more general somehow idea in algebraic geometry that we call gauge. And the French, I'm not very good at French pronunciation, but I think it means something like analytic geometry and algebraic geometry are somehow related in a sense over C or over say, yeah, over nicely algebraically closed fields like this. Okay. In other words, if we actually trace up a bit, so these things are the same. We had isogenies here, and up there we have that we take a complex number, and then what I do is I scale my lattice, and this lattice is then contained in the other one, a sublattice. So what this means is that somehow these numbers in C, yeah, such that the lattice is contained in here acts like an isogeny. And it actually turns out that if you consider the lattice C mod lambda, that all the isogenies of this lattice, yeah, again some surjective map, such that the origin is preserved, are really of this form. So these are really the isogenies of our torus. Okay, that's quite cool. Now, there's not, of course there's some name for this, and there's also something. There's a corollary written down in the notes, namely if I take E1 corresponding to lambda 1, let's take 2 corresponding to lambda 2. And we haven't really talked about when two elliptic curves are isomorphic yet. I hope we'll do that in the future, but I mean, it's not super hard to define. But let's just ignore that for now and say, okay, yeah, we knew whatever it means that two elliptic curves are isomorphic, but it turns out that E1 is isomorphic to E2, at least over C, if and only if lambda 1, lambda 2 are homophadic. And this just means that there exists some alpha in C star, because I don't want to send everything to 0, that would be silly, that lambda 1 is alpha lambda 2. Okay, so somehow, if you think about it, lambda 1 is maybe some two-dimensional subgrid of C. So all you could do is maybe you could stretch it a bit and rotate it, and then it would have to overlap with lambda 2. It just means that you take two bases for this lattice and they have to generate the same lattice. And these two bases, they need to be related by the action of multiplication by one complex element. So it's quite rigid. There's not much you can do in a sense. And I should say that this corollary actually will be important in the future lectures when we actually study moduli spaces of elliptic curves. Because when we talk moduli spaces of elliptic curves, then somehow the points in our moduli space, it will parameterize isomorphism classes. So it's good to know, because and the way we will do this is actually we will look at it from a complex perspective. We won't really talk about elliptic curves, but we will rather talk about the lattices. And so it's good to know for us when two lattices are isomorphic. And when two lattices define the same elliptic curve in terms of isomorphism, and that's namely when they're homophadic. But that will be maybe next or the lecture after. Depends on how fast we can go through this. Okay, now let's see. I think I talked a lot, but there's still a bit of time. So I will just I won't write down what this uniformization theorem means. I will just say it out loud. So there is a theorem called the uniformization theorem for elliptic curves, and it says that every elliptic curve over C is parameterized by elliptic functions. What this means is that every E over C, let me note it down just for completeness sake. So every E over C, every elliptic curve defined over the complex numbers, there exists a lattice as in theorem star. Okay, and we'll have to look at the script how theorem star was defined. And the nice thing is it gives you an equivalence of categories, but we just said that pretty much, right? So we have elliptic curves over C, and the morphisms are isogenies, and this is an equivalence of categories with elliptic curves over C, and the morphisms are analytic maps. Okay, such that we preserve base points. And of course, there's the third thing. Okay, I won't mention that anymore. So now in the last 10 minutes, I hope we get through all of that. I want to talk a bit in preparation for when we talk about complex multiplication. So let me quickly talk a bit more about torsion groups. They're really easy to understand for elliptic curves over C. So I take any E over C, okay, and turns out that I look at this set EM for some integer m bigger than 1. Now this set is defined as all the points such that if I add the point to itself m times, then it's 0. Okay, and this just means taking p plus m times. Okay, but if you actually look at this algebraically, right, we know that point addition is really given by some algebraic function. Okay, so multiplication by m again is an algebraic function. Okay, so you should really think of m as a morphism itself in a sense, and that's why. So first of all, a turns out that for elliptic curves over C, these torsion groups, they are very easy to classify. They are just two copies of the cyclic group of M elements. But again, I said this is actually a rational function, so I can actually define a degree in terms of algebraic geometry, and turns out the degree is M squared. Okay, that's pretty good, right? Because that also fits the size of this group here, if you actually think of the size of the fibers. So it, in a sense, it should be M squared. I mean, it's a bit of a fishy definition of the degree, but you know, if everything is nice and algebraically close, then it's actually true. In general, of course, you would have to take the proper algebraic geometrical definition of field extensions, but in this case it works out nicely. And so M, yeah, this is actually a map from E to E itself. So M should certainly be in the endomorphism ring of an elliptic curve. Okay, but now the question is, how big can this endomorphism ring be? Will it just be all the multiplication by M maps? Is there something more? Well, turns out there are two possibilities for elliptic curves over C. So if I take an elliptic curve over C, then I say that omega 1, omega 2 generate lambda corresponding to E. Then either. So either the endomorphism ring of E really is said, in which case it's really just these multiplication by M maps corresponding to every integer in set, or there's a second possibility. N of E is a bit bigger. N of E is actually isomorphic to some order in this imaginary quadratic extension of Q, and the extension is generated by omega 2 over omega 1. And this is an imaginary quadratic extension of Q. Okay? There's this weird word order here. I should probably quickly say what I mean by that. So if I take any number field, okay, certainly this is a number field, so take K a number field. But then that I mean some algebraic extension of Q. Then an order R, okay, yeah, this is a subring of K, which is finally generated as a Z module, which is finally generated as a Z module. Okay, and you also want that if you extend by scalars up again, then you land in your quadratic number field. So you also want that R with Q is K again. And one way to think about this, take any number field, think of its ring of integers. It's certainly an order. Think of the easiest one. Maybe take Q, the ring of integers is just Z. This is definitely an order. Maybe think of Q adjoint, I don't know, I, then probably ZI, this would be an order, and so on and so forth. Obviously, if things get more complicated, it won't be as nice anymore, but this will be true, I guess. Now, we have 3 minutes left, and I think I will skip the proof of why this is true, but you can read it up for yourself. It's quite cute, and yeah, in the end, the key step, I think, is this theorem triangle, which we called, namely that. So I just sketched the key step because I think this is quite cute. So what you do is you define this ring R of all the elements in C, with alpha lambda is in lambda, right? So it turns out that the endomorphism ring of E actually has to be this R. Okay, and this really follows from this theorem triangle we saw earlier. If you think about this, these are just all the isogenies that send you to yourself, and then it's just about classifying which form this can have, right? And either R is an integral extension of Z, sure, or again R is integral over Z, and then you show that R is in order. Either R, well, it follows that either R is Z or R is order in tau, where tau is such that lambda is 1 constant. Okay, and the way I get this actually is by just normalizing. Well, I can just divide everything by omega 1. Yeah, and I call this tau, right? Because this is certainly these two lattices actually homophatic. So they define the same elliptic curve. And well, showing this is basically looking at quadratic equations. That's not hard anymore. It's just thinking about what happens, how two of these lattices can be related by looking at these alphas. Yeah, and one final note I want to make really quickly. So in this case, we somehow talk about ordinary curves. Okay, so there's nothing special about them. The endomorphism ring is just, whatever you think it is. But in this case, we say that E has complex multiplication. Okay, and this is a bit giving, this should give you a bit of a gusto about talking about complex multiplication later. So complex multiplication means something entirely different than the word says. Okay, it doesn't mean that you can multiply things by complex numbers. It really means that somehow the endomorphism ring is larger than for ordinary curves, right? So the endomorphism ring here really has extra elements that are not just multiplication by n. Okay, I think that's all I wanted to say. Good.
Thanks a lot, Lucas. That was good.
Yeah, do you have any questions? And pretty much all I talked about you can find in Silverman again with a bit more words, I guess. But I mean, yeah, he explains things differently. I mean, or otherwise just ask now. Yeah.